Right, hello. Welcome to the first lab, the flood lab. This is your first coursework. So today we're looking at what happens to a structure when it's under flood, so flood from water, namely. Let's first think about the hydrostatic forces that it may be subject to. So you have a water flow, so we're talking about the water surface here. As the water flood approaches our structure, it's forced to a stop. The actual flow becomes zero. And we can calculate the hydrostatic force using a version of this equation here. I'll go through that in a second. And we can calculate that at being maximum at this point, 1/3 above the base of the structure. So let's see how we calculate that force. So the force is FH, the hydrostatic force, is equal to 1/2 times rho, the density of the fluid. For this, it'll be 1,000 kilograms per meters cubed, multiplied by gravitational acceleration, which is going to be 9.81 meters per second squared, and then multiplied by this bracketed fella here, which is the height of the water at the front of the structure minus the height of the water at the rear of the structure. And then obviously, to turn it into a force, we have to multiply it by that third dimension, which is the width of the structure. This image is in 2D, so our width would be per unit width, it would be 1. So this height here is HA. But as the water passes the structure, okay, it reduces to 0 at this point, but some of it is forced around the side. And we have a surface profile similar to this. And so we would have a height of water at the rear, HB. So actually the resultant hydrostatic force is FR is going to be the hydrostatic force from this side minus that side. So it's actually just this little bit here. And so that's why we form the equation like this. It's a shorthand version. You've got HA squared minus HB squared. That's the hydrostatic side of things. But a structure under flood is also going to experience a hydrodynamic force, which is this second equation. F dyne is equal to 1/2 times rho times C sub D, which is the drag coefficient, multiplied by the height of the water, the width of the structure, and the velocity of the flow squared. Now, for a square-shaped structure, the drag coefficient is usually 2. So what happens in this case, we have, I'm going to use the 3-dimensional version here, a flow of water approaching our structure. It reduces to 0 at this point, but some of it is then forced around the side like this, and then downstream. In that, the drop in our free surface profile is a result of an acceleration of the flow. So if we think about our continuity equation, our total discharge per cubic meter per unit time is equal to the velocity of the flow multiplied by the area of which that flow is flowing through. And in this case, it will be a channel. It'll have an area like this, add whatever the area of the channel is as well. Now, essentially, as soon as you put an object in that flow, you're going to reduce the area. So in order to have continuity in discharge, Q, you must therefore increase the velocity. So this is why you get an increasing velocity around the side, and as a result, you get a drop in water height. Right, welcome back. So this is coursework 1, and this is the actual flume that we're going to be working with. So this is the flood lab. We're talking about what happens to, what are the forces on structures when they are under flood. So what we've got here is a recirculating flume. It's discharging a constant flow velocity down this channel, recirculating it back. So we have a nice controlled flow. You could calculate the velocity in this flume by using the continuity equation. You can say, well, what is the discharge is equal to the velocity times the area. So a rearrangement of that equation, Q divided by A is equal to U. So all you'd need to know is what the area of the flow is, what the discharge is, and then you can actually find out what the velocity is at any point. The discharge will be given to you for the coursework, but in here we'd measure it using a weight bench. The area is important for this demonstration. It's going to change. At the moment, it's the area is the height of the water and the width of the flume, the area of that channel. Now, I'm going to add in our first building, as it were, and I want you to just look at what happens to the flow as it meets that building and is forced to move around it. So, right. So broadly speaking, the flow height on this side is increased, you'll have noticed. Why? Because there's an obstacle in the way, and therefore it's going to slow down, so the velocity is going to drop, and therefore the height's going to increase. On this side, the flow height is much lower. And again, why is that? Because we've had an acceleration of flow around the back, and so the velocity at this point is much higher than it was upstream, and therefore the height is much lower. Now, in the other camera angle, you can see that the flow is doing what that I drew for you on the whiteboard earlier. It's sort of going down like this and then out like this. Now, the flow eventually recovers because this is the same width as it always was, so the flow will recover further downstream here. What are the forces on this structure? Well, you've got a hydrostatic force due to this height of water, 1/2 times rho times g times h times the area, which is going to be the height of the structure and the width of the structure. So you've got a hydrostatic load vector, maybe 1/3 from the bottom, applying that way, trying to push the structure over. But you've also got the hydrostatic force of this height of water on the back. Now you're probably thinking, well, isn't that water moving that way? So the force, there shouldn't be any force, but no, remember this is the hydrostatic force. So that water, the pressure from that water is applying a force this way. So the total hydrostatic force is going to be that minus that. It's about that, okay? There's also that hydrodynamic force, and that's due to the drag coefficient of this, which is about 2, because it's a bluff body, and the acceleration of the flow, so the velocity of the water, at the side of the structure. And that's going to be faster than it was upstream. So you've got hydrostatic force, hydrodynamic drag. So we've identified that, a structure under flood is undergoing these forces, so we're going to have to build it to withstand those forces. But what could you do as a civil engineer if you're designing a built environment, it's not just a single structure, in order to try and reduce the effects of any flood that might occur? Now, usually when you build buildings, you build them in rows, there'll be a street, there's blocks, etc., etc. There's not often one building on its own. So let's add in another building, a little analog of a building. I'm going to add it in about this point, and I want you to observe what's happening to the flow height. Now, it all happens rather quickly, but you can see this height got bigger. It's almost the same as it is at the front here. Now, is that actually what you thought would be the case? Because when we think about what's the hydrostatic force on this structure, that first structure now, it's actually less than it was when there wasn't a building behind it. You'd have thought, or we often think, that the building in front is the one which is most at risk. But to reduce the hydrostatic force on the building in front, you actually need a building behind it in order to, back that water up, slow that water down, equalize this hydrostatic differential. So now the hydrostatic load is this one minus this one. If you look closely, it's only about that much, 0.5 centimetre in this setup. It's quite a low force. Also, that means that the drag is lower as well, because the acceleration of flow is lower. So it's all good for this front building, but this one's suffering quite a bit. Okay, I would say it's even worse than it was when there was only one structure. You're backing up quite a lot more flow. You're forcing it to accelerate quite a lot more. So let's have a look and see what happens if we add a third building. So again, let's watch what's going on. So, again, it kind of happens gradually. It's like a pulse that comes backwards, equalizing that flow height. The flow velocity is dropped, it's not as high as it was. And the load on this second building is now much lower. The load on the one at the back is quite significant. So effectively you're always going to put the structure which is most at rear at most risk. But actually that's not what's going to happen in real life, because actually in real life, if this was a flood or a tsunami or something like that, it's not a constant discharge. This is a flume where it's a constant discharge. So by the time the flow's got to the back of your built environment, it might already be losing energy and velocity as well. So the interesting thing about this setup is, perhaps counterintuitively, if you want to protect a building from that hydrostatic and hydrodynamic load, it's a good idea to have buildings behind it rather than just in front of it. There's other things to think about in this when it's in the real situation. You've got debris as well, floating cars or trees or whatever it is that might impact your structures. And in that case, the building in front is always the one which is most at risk. Can be most at risk. Okay, another thing you could think about as an engineer is maybe you stagger your building, so you could move this from the other side. Perhaps that changes things. I actually think it looks like it's a little bit worse. Why would it be a little bit worse? Well, when you're thinking about the channels, when they're all in line, you've got a free path for some of those fluid particles to go down. Now you're actually blocking all the fluid particles in your channel. So it's actually more of a blockage than it was when it was on this side. And again, for debris, that'd be even worse, because debris would be hitting here and it gets stuck here and gets stuck again down there. If you leave a space, the debris might just go straight through. Okay, a little bit of food for thought and some demonstration there for you. Okay, and that's the end of this demonstration.